So hello, good morning to everybody again, and here I'm going further with our lecture, and so our lecture now concerns the relationship between monotonicity and limits and also continuity, since we introduced the continuity, and we know from the study of sequences that monotonicity is linked to regularity. So when something is monotone, in particular a sequence is monotone, then there is a limit, and the same will hold for functions. So the title of this chapter is Limits, Continuity, and Monotonicity. So we know what is a monotone sequence, we don't know what is a monotone function. So let me first define a monotonic function. And so we start as usual by introducing a subset E of the real line. This subset has to be non-empty, and it is the domain of the function f. So function f is called as monotonically increasing if whenever you take 2 points x and y in the domain of the function with x less than y, then you have that f of x is not larger than f of y. Again, notice that here there is also the equal sign. Okay? This you have to know because some theoretical questions in the written exam ask to really give the correct definition of monotonicity, and in monotonicity you have to take into account also the equal sign, while in strict monotonicity the equal sign is not there. Okay, this is a matter of definition, but you have to know that. So to fix the idea, I give you a pictorial example. So consider again this situation here where you have a graph of this kind. Then you have, for instance, a jump, and then a thing like that, and then again a jump, and then a constant part, and so on and so on. This is an example of a graph of a monotonic function, monotonically increasing function. Sorry. And a remark, I can propose you is that constant functions are monotonically increasing. graph of constant functions are horizontal lines. Okay. And now, let us define here also the counterpart, so to say, monotonically decreasing function. I just copied a definition of monotonically increasing function. And here, again, I have a domain E, subset of R, non-empty, and the function is called monotonically, this time will be decreasing. If, whenever I take x less than y, then what you have here is that the image of the larger point y is not larger than the image of the shorter point x. Okay. And other definitions can be easily obtained by this cut and paste. And for instance, here I can introduce the definition of strict monotonicity. So f is called strictly monotonically increasing. If for every couple x and y with x less than y, here we have that f of x is strictly smaller than f of y. And so in the same spirit, we can introduce the definition of strictly monotonically decreasing. So here, this is strictly monotonically. Function is strictly monotonically decreasing if, again, for every x and y in E with x less than y, then the image of the larger point y is smaller than the image of the smaller point x. So I wanted to give you this collection of definitions in quite a pedantic and long and boring way, but you have to know them very well, okay? It is intuitive. The only thing you have to remember that if it is not strict monotonicity, then you have to include your definition, the equal sign. Okay? And if you don't want to introduce the equal sign, then you have to refer to strictly monotonicity. So, just a stupid remark. I say that one often refers to monotonicity, not in the whole domain of F, so for functions on subsets of their domain. For instance, let us take the very well-known parabola. F of x is equal to x squared is monotonically strictly increasing, for x larger than 0, and f of x, equal to x squared is monotonically strictly decreasing. Or you can also include 0 here, is monotonically strictly decreasing. For x less or equal 0. Okay? On the other hand, if you have f of x equal to x to some odd power 2m plus 1 with a natural number n, this is monotonically strictly increasing on the domain R. Other functions, for instance, e to the x, log of x, hyperbolic sine of x, I remember what is the definition, is equal to e to the x minus e to the minus x divided by 2. Then the arctangent of x, hyperbolic tangent of x equal to e to the x plus e to the minus x divided by e to the x minus e to the minus x. All of them are monotonically strictly increasing on their domain. Monotonically. And of course, sine of x is monotonically increasing, but not strictly. And moreover, another statement, it is if f is monotonically increasing, and you can also say strictly, then minus f obviously will be monotonically decreasing and possibly strictly. Then if f is monotonically strictly increasing, then you can easily prove that f is invertible and f minus 1, which is not 1 over f, it is the functional inverse of f, is again monotonically strictly increasing. This is very important to not think of the logarithm and of the exponential. Okay? And now after these examples, and let me give the fundamental theorem on monotonic function, and which links monotonicity and limits, like in the case of sequences. So theorem. Monotonicity and limits. So again you have E in R, F from E to R monotonically increasing, and then consider X bar be an accumulation point of E such that for every W, which is a left neighborhood of X bar, there are always points of E in W beyond the point X bar. So I'm saying here that, so roughly speaking, I am saying in quotation mark just to stress the fact that I'm saying a sort of formal things, okay? A thing that is not really completely rigorous. So that X bar is a left accumulation point of E. I do that because in this way it is possible to study the limit from the left. So then, whenever it is possible to take the limit from the left, this is the philosophy of the theorem, we have that the limit for x going to x bar from the left of f of x is equal to the supremum of f of x, where x has to be taken, of course, in the domain of f in order to be able to write f of x, and x is less than x bar. So again, this is a remark, this deserves a remark. And the remark says that, like for sequences, I am saying that monotonicity entails the existence of the limit and in the case of monotonically increasing function, and the limit from the left, such a limit coincides with a supremum of f in the appropriate set. Okay, the picture here is the picture. So here is x bar, so we can consider a monotonical increasing function like before. Here we got x bar, and so on and so on. So let me magnify in a neighborhood of x bar what happens. Very, 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 very bad. But we can easily write like this. Okay, so let me magnify what happens here around x bar. So here in x bar there is a jump, but this is not very important because I'm taking the limit from the left, so I'm here, I'm following with the function here, and I say that here the limit is this guy here. This guy is the limit for x going to x bar from the left of f of x. Very good. And so this is what the limit says, regardless of what happens at x bar or at the right of x bar. From the left, if monotonicity increasing is fulfilled, you have the limit, and the limit is the supremum. And okay, let us go with the proof. Then I will postpone some comments. Proof. So take x bar in the E. So, such that for every W, which is a left neighborhood of x bar, W intersection E minus x bar is not empty. So sort of what I called left accumulation point. And consider xi, call xi the supremum of f for x less than x bar, x in E. The supremum is meaningful. Is meaningful because there are points of this kind, since every left neighborhood of x bar hosts some points of it. So this set here is not empty. So the supremum is well defined. Okay? And again, we consider the case of psi is a real number, so it is not plus infinity. And let epsilon be an arbitrary number larger than 0. Then, by definition of supremum, there exists an x tilde in E with x tilde less than x bar, such that when I move psi towards the left of a quantity epsilon, f of x tilde is larger than psi minus epsilon. Moreover, so then let x be in the set x tilde x bar, and of course in E. Again, this set is not empty because x bar is a left accumulation point of the set E. So since f is monotonically increasing, one has that psi minus epsilon is less than f of x tilde. This is the definition of sup. Here we use the fact that it is monotonically increasing because, this is less than f of x, okay, by monotonicity. Since here we know that x is larger than x tilde, and of course this is less or equal psi, while psi is the supremo and x falls here in a set which is included in the set that defines psi as a supremo of the values of f, and obviously psi is less than psi plus epsilon. So we found that for every epsilon larger than 0, there exists a left neighborhood. This is the left neighborhood of x bar, such that all points in the left neighborhood here and in the domain have an image that fulfills this: psi minus epsilon less than f of x less than psi plus epsilon. I just want to stress here what I'm using now. I'm using this chain of inequality I put in evidence with orange color, and so at the end, by definition, of left limit, we end up with the fact that the limit for x going to x bar from the left of f of x is equal to psi, which is equal to the supremum for x in E, x less than x bar of f of x. This is the end of the proof, and this is also the end of this video now, and let us go for the other video in some